Okay, all right. Well, it's the home stretch. We are almost down to the last week. So chapter 7 today, BJT amplifiers, kind of continuing on from chapter 4, which is BJTs. And we looked at the common emitter design on Monday. And the reason we do that is because we have an early lab in the week on Tuesdays. But now we get to the actual explanation. So, okay, so common emitter amplifier. Oh, this is a BJT amplifier, common emitter because the emitter terminal is common to the input and the output. Okay, so few things before we begin. Oftentimes you would have seen circuits with notations like these. Simply have VCC, perhaps a resistor, emitter resistor. It's indicated by ground. Base resistor RB. And we'd display this by VBB. So biasing voltage is VBB at the base, VCC at the collector, and emitter resistor connected to ground. The circuit is exactly the same as this one, okay? The only difference is that the other connections, the ground connections, the input and output voltages are implied. So as an electrical engineer, you should be familiar with all of these circuit diagrams or notations. Okay. Now, VCC is between collector and the emitter in our diagram. There is no emitter resistor. Simple biasing circuit. RB could be a voltage divider bias, as we saw in the previous class. RB could be R1 in parallel with R2, okay? But we are not concerned with that right now. Okay, so in order for this BJT to work as an amplifier, first of all, we must bias the BJT in the active region. So the DC voltage is being applied must bias or must set the bias in the active region. Okay, in the active region of the BJT operation. Not cutoff, not saturation, but in the middle of the active region. Then the input signal must be sent into the base. Okay, so the input signal V in or V in of T, the AC signal, is sent into the base. Some authors like to use the word injected. So the AC signal must be injected into the base. Now, when you send it into the base, the signal must be small enough to not shift the biasing point away or outside of the active region. Okay, so the AC input signal must be small. If it's large, then you would either have cutoff or saturation. Either the positive or the negative peak of the signal would get cut off at the output. So the signal must be small. Yes.
Very far away from our
And we'll see that. We'll see all of that in the next few slides. So the input is sent into the base, and that input must be small. Another reason for that is we will look at small signal analysis. Okay. So when we say the input must be small, that is one reason. The other thing is BJTs, diodes, MOSFETs, FETs, they're all nonlinear devices. Okay. But we apply linear circuit analysis techniques to these nonlinear devices. And the way we can do that is if we model a very small portion of the characteristics. So any nonlinear device can be modeled as a linear device if you take a small enough slice, and then we can assume that that small portion is linear. And hence, we can apply a linear circuit analysis techniques to these nonlinear devices. Okay. And that analysis, we will see later on in this chapter, is known as small signal analysis. Okay, small signal analysis. And so we'll have, there are several different models, but we'll look at one of the most common and popular ones later on in this chapter. Okay, also regarding the voltages and currents. If you think back to chapter 1, we talked about how the voltages and currents that are flowing in these circuits are a combination of the DC and AC voltages. So when we apply voltages from the DC bias and we apply the AC input signal, all of these combine together to give us the voltages at the terminals of the transistor. So VB, lowercase v, and uppercase B, which is a combination of the AC voltage plus the DC biasing voltage VB. Similarly, current IB, total current IB flowing into the base is a combination of the AC input current IB and the DC current from VBB. The output is taken directly across the collector. In this case, we are taking it directly across the collector to emitter junction. And so our output, V out, is basically VCE. And that again is a combination of the AC plus DC. Okay, AC plus DC. And V in, V out, they all have a common connection. If we have a ground, we connect it to ground. And so VCC, VBB, V in, V out, they're all referenced to a single common point. And the reference point is shown here. Okay, single reference point for all quantities. Okay, so then let's look at our example. Here we are provided with a circuit with RB, RC, VCC, and VB. Input characteristics are shown here. Output characteristics right here. Input is into the base, so the input characteristics is basically the base current IB as a function of the base emitter voltage VBE. So in terms of voltages and currents, we say IB is the input current and VBE is the input voltage. Okay, again, input is going into the base, so the input characteristic is the base current IB as a function of the base emitter voltage VBE. On the output side, we are taking the output at the collector, and so it's a characteristic of the IC, the collector current IC as a function of collector emitter voltage VCE. Okay, VCE. So we are given the characteristics of this transistor BJT. If you look at the output characteristics, these are values for IB, the input current IB, and IC values are given here. So we can calculate the forward beta gain as IC over IB. In this case, it's rather straightforward. We can pick any value and we can have 2 milliamps divided by 20 microamps. Or we can choose 1 milliamp divided by 10 microamps. All cases, it comes out to an even round number of 100. Now, what we will do is we'll perform load line analysis on this. Okay, the characteristics are given to us, so we'll write equations and we'll perform load line analysis. And we'll see how we can transfer the input to the output. Okay. So to write or to generate our equations, we fall back to our linear circuit analysis techniques. In this case, we want voltages, so we're going to write KVL equations for the input and the output. So if you apply KVL for the input loop, we have, how many voltages do we have? 1, 2, 3, and 4. Okay, 1, 2, 3, 4 voltages. So typically what I do is I apply KVL, and I think I mentioned this in the first week of class. You do not have to follow my method. At this point, all EE students are familiar and comfortable with their own methods of applying KVL, so I'm repeating that again. I apply KVL clockwise, starting from the bottom left corner. And so for me, KVL would be minus V in of T plus VRB, the voltage drop across the resistor RB. That would be the DC voltage drop, plus VBE, again, the DC base emitter voltage, and minus VBB equal to 0. All voltages should sum up to 0. Okay. Now we'll rearrange the terms. So we have the inputs on the left side and the other voltages on the right-hand side. So I will have V in of T plus my DC voltage VBB, DC biasing voltage VBB, as equal to VRB and VBE. Okay. V in of T plus VBB is equal to VRB plus VBE. Now, I haven't mentioned the values that are given to us in the example, but if you're trying to analyze a circuit, everything will be given to us. We are simply calculating the output. Okay. So at this point, V in of T would be given to us. VBB would be given. And VRB we can calculate because RB would be known to us. So all of these values known or given. Okay. They are known values. VRB is, of course, IB times RB. Okay, IB times RB. So we have to calculate. And I'm going to replace VRB here with IB times RB, voltage drop across the base resistor. So now that I have my KVL, I want to generate my load line. I'm going to substitute. I need to find IB and VBE. So I'm going to substitute first. IB is equal to 0. And therefore VBE would be equal to VBB plus Vin, or Vin plus VBB. Right? If IB is 0 amps, then VBE is simply the DC bias voltage plus Vin of T. And if VBE is 0, then IB is equal to VBB, VBB plus Vin of T divided by RB. Right, standard method of generating load line. Apply KVL, and then substitute X and Y axis values equal to 0, 1 at a time to generate the other values. Okay, so far so good. Yes. Mm-hmm. Mm-hmm. Where? No, because VBB is being applied. That's the DC biasing voltage, so it won't be 0. Yeah, that's the biasing voltage. VB would be different. VB is the base voltage. That would be different. Okay, so let's see. Okay, so we have our load line. So load line would be, as I was saying, VB, it would be on the input characteristic, and I have it on the next slide. But let's consider if V in of T is 0, meaning you're not applying any AC input voltage, then what do we get? If there is no AC input voltage, meaning if V in of T is equal to 0, then VBE is simply VBB, and IB is simply VBB or RB. Okay, so that gives us our Q point solely due to the DC biasing voltages VCC and VBB. Okay, that gives us the 2 points on the load line. VBE would be equal to VBB, and then IB would be VBB over RB. And so you can see how the load line is influenced by the chosen value of RB. RB and, of course, biasing voltages VBB. Let's do the output KVL. So KVL for output. And the output side, you only have 3 voltages. It goes through here. So 1, 2, and then if you have RE, you would have a 4th voltage. But in this case, we are not using an emitter resistor. So it's 2 drops, and it's VCC. So VCC is simply divided across RC and VCE. So I would write minus VCE minus VRC plus VCC is equal to 0. And so if I want to obtain an equation for VCE, rearrange the terms, and VCE is VCC minus the ICRC drop. The voltage drop across the collector resistor. And this equation is key in why we have a phase shift of 180 degrees. We'll see that in the next slide. So this is our KVL equation or expression for output voltage, VCE. Now, to find points for the load line, if VCE is equal to 0, then IC is simply VCC over RC. And if IC is equal to 0, then we have VCE simply equal to VCC. Right, output voltage goes directly to VCC. So some groups, when we are doing the lab, if you remember, you don't apply an AC signal, you'd obtain a flat line at your VCC, the output. That is why. If there is no input, then IC collector current is 0. Collector current is 0. Your output goes max VCC, flat line. Okay, so now we have our load lines. We go ahead and plot those. And so if you plot it on the input, actually, we don't yet have a load line, sorry. Need to do one more calculation. So in this example, we are given some values. And the values are VCC is equal to 10 volts. VBB is equal to 1.6 volts. Base resistor RB is 40 kilo ohms. And RC collector resistor is 2 kilo ohms. Okay. So now we will generate the exact values based on the load line equations we have from the previous slide. Vin of T is given as 0.4 sine of 2000 pi t volts. Circuit does not change the frequency. It will affect the magnitude of the signal. It will affect the phase of the signal, but it does not change the frequency, does not affect the frequency. So we are not concerned with the phase, not at this point yet, and we are not concerned with the frequency. We are only concerned with the peak voltage. And the peak voltage is 0.4 volts. Frequency, we are not concerned, but it is 1 kilohertz, 1000 hertz. So if one peak is 0.4 volts, then the swing of the signal should go to plus 0.4 volts and minus 0.4 volts. So the input is changing between plus 0.4 minus 0.4. So V in max is plus 0.4 volts and V in minimum is minus 0.4. Okay, AC signal, small AC signal being injected into the base or sent into the base. So our input KVL was IB is VBB plus Vin of T divided by RB. Okay. If Vin of T is 0, meaning it's just the DC voltages, just the biasing voltages, then IB, and this would be the Q point, right? We are not applying any AC voltages, just the DC. So subscript of Q, IBQ, IBQ would simply be VBB over RB. And that would give us 1.6 or 40,000. So 40 microamps. 40 microamps. And that point is right here. IB value. This is the load line for DC bias. Okay, that's the load line for DC bias. The other point, I'm going to write it down here, would be VBE VBB plus Vin. And if Vin of T is 0, then VBEQ is simply VBB. In this case, it is 1.6 volts. And that point is right here. So that's our original load line. The original DC load line that is at 40 and 1.6. Okay, 40 and 1.6. How are we doing on time? It's good. So far, so good. Okay. Then let's find the other load line. So now the input is swinging, right? You have our load line. You have our DC load line. Now what happens? You apply a AC signal on top of our DC biasing. Because of the applied AC voltages, the value for IB and VBE will change. And if IB and VBE are changing, the load line shifts up and it shifts down. So it swings above and below the DC biasing load line. Here and here. Does that make sense to everyone? We have our DC biasing voltage. We have a DC load line that is solely from the DC voltages VCC and VBB. Now, if you apply an AC input at every instant in time, that AC voltage, if you just analyze a small piece of the AC voltage, let's say a single moment in time, at a single moment in time, that AC voltage has a single value. It's a function of time, but it has a single value at any single point in time. And then the DC load line changes. It goes above and below. And so you have two more load lines signifying the max and the minimum value of V in of T. So your input signal is swinging between those max and minimum load lines. And so we must find the values of those load lines. And that is easily found by plugging in the values of V in of T. So IB max would simply be 1.6 plus 0.4 divided by 40,000. And that gives us 50 microamps, 2 divided by 4. And then IB min, the lower swing would be 1.6 minus 0.4. That comes out to be 1.2 divided by 4, so 30 microamps. And those are given right here. So 30 minimum, maximum. And the corresponding VBE values VBE max is simply 1.6 plus 0.4. So it gives us 2 volts. And VBE min is 1.6 minus 0.4 gives us 1.2 volts. Those are the x-axis values. And so here, this is the max, and this is the min. And so we have 2 more load lines, and our input signal is varying between these load lines. And the intersection point, these load lines, right here, and right here, gives us the 3 Q points for our input side. Okay. Q max, Q min. The input actually would be varying something like this. Actually, let's not draw. Let's hold off on that. But the 3 load lines, those 3 load lines is the maximum swing of the input voltage on the input characteristic. Good. And now we go to the output characteristics Output characteristics are here. We are already given the output characteristics. We also have the output load line, and the output load line so this is output. VCE is equal to VCC is equal to 10 volts. And IC is simply VCC over RC. So 10 divided by 2000, 5 milliamps. That's the x-axis value, and this is the y-axis value. Okay. Now, there is no Q point on the output. Output does not have those Q points, right? We want to translate the input. We want to transfer the input to the output. So what are we going to do? We are going to find the Q point on the output characteristics, which is right here, 25 microamps. We are straight away going to find the intersection of the Q point on the three values of IB that we found. If I plotted them side by side and resized it so it's to scale, essentially what we are doing is we are looking at these points right there. And those three intersection points give us the output swing of VCE. Okay. I should have wiped these out before. Anyway. Q max and Q min. But the three intersection points give us the output voltages of VCE. And so VCE is swinging between 3 and 7. The intersection of the load line, the output load line, the intersection of the output load line with the output characteristics gives us our output. And that is the load line analysis. This is how we find the output voltage using load line analysis. Okay. Graphically, this is what's happening. We are applying and of course, this is not to scale because all right, let's just what the that's what, yeah, thank you. All right, so this is our input waveform, V in of t. Okay, V in of t. What do we see? V in of t is only varying between this line, which is 35 microamps and 15 microamps. Very small signal, very small IB, very small IB. Look over on the input side. How much is VBE changing? Very, very little. Maybe 0.01, 0.02 volts perhaps. So very small change in VBE gives us a significant change in VCE. So in terms of just the current, we have a small input current of 15 to 35 microamps, giving us a IC value between 1.5 and 3.5 milliamps. So input current is IB, and it has a range of 15 microamps to 35 microamps. So small that we would not even be able to measure with standard lab equipment or lab techniques, not without like large resistors and stuff. And output current would be IC, and IC is bringing from 1.5 milliamps to 3.5 milliamps. Obviously, these are like ideal characteristics, for example, but with real life VJTs, we have a slope. The beta also increases, but does this make sense? Right? Very small input current change results in a very large output current IC. Also, look at this. When VCE, I need to change this actually. Right? When IB, the input current goes max, the corresponding right here. So this gives us this point right there. When IB, the input current goes max, you have VBE also at max and VBE min. Okay. So max value of IB gives you max value of IC. 35 microamps gives you 3.5 milliamps. Current gain of 100. Look at VCE. VCE is minimum. Hence, 180 degrees out of phase. And we can see that from the equation also. I will just show that in a moment. All right, so input voltage is VBE. We can calculate that, but I want to say approximately swing of, I don't know, 0.6 to 0.7 perhaps. And then output voltage VCE goes from 3 volts to 7 volts. 3 volts to 7 volts. Actually, I would say 7 volts to 3 volts because it's 180 degrees out of phase. But anyway, we saw that the gain of the CE amplifier was minus RC or RE. You know, the minus, of course, indicates it's out of phase. Does all of this make sense? What doesn't make sense?
Okay.
So let's look at when V in is 0, what is our output? VCC, right? If V in is 0, sorry, not VCC, a VBQ. But look at our output equation right here. VCE is our output. That's the voltage, the collector to the emitter. The current is coming from VCC in this direction. Voltage drops across RC. If IB is 0, then IC is 0. If IC is 0, there is no voltage drop across RC. So IC RC is 0. output is VCC, max output. No input, max output. Now, if you apply input, input goes max. If input goes max, meaning IB goes to its maximum possible value. So IC goes to its maximum possible value. If IC goes to its maximum possible value, then this drop goes to its highest point. Hence, VCE goes to its lowest point. So as the input increases, the output voltage decreases. And hence, 180 degrees out of phase. Remember, a couple of classes ago, I stated we can think of amplification as the summation or the multiplication of AC with DC. In reality, what is happening is you have your DC flat line, and it's taking on the shape of your AC input. So if there is no input, the output is the shape of the DC, which is a flat line. Yes. Current gain is beta. Voltage gain is different. Voltage gain depends on the biasing.
Okay, assuming we're in active, like right? IC is beta IB.
Beta IB, yes, beta IB. So our range depends on beta times IB times RB, yes and no. So let me explain. So the question being asked is about how RB affects our output.
RC affected, right? But how does RB?
Sure. Yeah. All right. So RB, let's say this is not, let's say this is our input side. Okay. This is the voltage divider bias. So R1, R2, and this is VBB. All right. Now RB, this is of course going into the base. And so this point is VB, the base voltage VB, right? And RB is R1 parallel R2. Now, whether RB is a single resistor or whether it's made of R1, R2 it's irrelevant, okay? We have a single resistor RB going in there, but since we are talking about how it affects it, let's also talk about the voltage divider biasing. So if R1 and R2 are equal, RB is R1, R1, R2, R1 divided by half of R1 and R2, right? Now, as RB increases, and I'm going to write it in shorthand. So as RB increases, the Q point is going to move down. Because if RB increases, your IB is now decreasing, right? Ohm's law. So if RB increases, IB decreases, so your Q point, your load line moves down. If RB decreases, what did I say first? If RB increases, then our IB decreases and moves down, and the reverse happens when it increases. Okay, so then it moves up. So your biasing affects the Q point, right? The biasing affects the Q point. So as RB increases, the Q point moves down and moves down the load line. Okay, and as RB decreases, then the Q point moves up the load line. So if you're biasing this, and you have, let's say we had a line like this, right? And then we had a line, load line, and I'm just drawing it randomly right now. If your Q point is up here, and you translate it here, now your Q point is got here. And if you now apply your input, and this is the reason the top will get chopped off, the input gets chopped off, so your output, the negative cycle, gets chopped off. And if the Q point is somewhere down here, then the opposite happens. Your positive half cycle is fine, but the negative is beyond the transistor's capability. And now, let's get rid of this. This negative would be fine. The positive would be chopped off. So what happens is, because of the biasing, the Q point is shifting, or it's forcing the transistor either into saturation or it's forcing the transistor into cutoff. So even though the actual Q point, the DC Q point, is in the active region, but because it's at the extreme, or maybe just closer to cutoff or saturation, when you apply the AC input, your output is now forcing the BJT to going into cutoff, into saturation, or it's forcing it into cutoff. So this distortion happens because it's now in saturation and it's now in cutoff. And so that's why biasing is important. We want it to bias the transistor in the middle of the active region. If taking this one step further, I have just a few minutes left. Voltage divider biasing. RB is parallel to, RB is equal to R1 parallel R2. So if you're using two resistors, and if R1 is much, much larger than R2, then your VBB decreases. VBB going into the base, or base voltage VB, decreases, right? Actually, let me write it this way, because this is going into the base for a voltage divider network. So your VB decreases because R2 is less. And if VB decreases, then IB decreases. If IB decreases, you're moving down. And if R1 is far less, or maybe if R2 is far more than R1, then VB increases, and therefore IB increases. And now you're moving up, or shifting up the load line. So your Q point changes. That's why biasing is very important. Okay, we have a few more minutes. Questions? Did all of this make sense? Does a lab make more sense now? That's why I don't prefer Tuesday labs. Repeating the same thing again. Because we can have at least two more classes if it's a Thursday lab. Anyway, questions? Okay. That's it. All right. So then we'll end class here today. Yeah, we are there's about a minute left. I want to talk about coupling capacitors, but we'll leave it for Friday. All right. So we'll end class here today, and we'll pick up here again on Friday. Yes. So I will post a reading assignment and a homework assignment for Friday. I was thinking of doing something for Thanksgiving week. I'm going to be working through. I want to make the students work through.